The working principle of transformer. Actually, transformer is a machine, but it does not have any moving part. That is why a transformer is referred to as a static machine. A transformer has three main parts: two windings and a metallic core on which the windings are wound. Windings are in the form of coil made of a good conductor of current. The windings of a transformer play a main role in the machine. The winding coils behaves as an inductor when an alternating current is allowed to flow through any of the windings. There will be an alternating flux produced surrounding the winding. The magnitude of this flux is proportional to the magnitude of the current flowing through the winding. The direction of the flux is according to the directions of current. The directions of the current in the winding can be found out by applying right hand grip rule. This rule states that when we grip a right hand with stretching the thumb along the axis of a coil or winding and other four fingers along the directions of current in the coil, then the thumb indicates the directions of produced flux inside the coil along the axis. Thus, flux becomes maximum in magnitude when current reaches its maximum for one cycle of the alternating current wave. The flux becomes zero when current in the coil crosses zero axis. Again, for next half cycle, the flux becomes maximum, but in opposite direction when current reaches its reverse maxima in this way. Alternating current produces continuously varying flux surrounding to the winding. The flux lines link the winding itself and the flux is varying, so there will be self-induced EMF across the winding. This phenomenon is due to Faraday's law of electromagnetic induction. This induced EMF or voltage, whatever you say, is same in magnitude and opposite in polarity of supply voltage applied. Alternating voltage causes alternating current in the winding, which produces continually varying flux inside and outside the winding. This continually varying flux produces induced EMF across the winding. So we can say that the supply voltage is caused an induced voltage. The winding is an effect of this cause. Hence, according to Lenz's law, this induced voltage will be in opposite polarity of supply voltage. Since according to Lenz's law, effect always opposes cause this self-induced voltage across the winding does not depend upon the number of turns in the winding but depends on the supply voltage. Where the voltage induced per turn depends on the number of turns in the winding. This is nothing but induced EMF divided by the number of turns in the winding. We have said that there is another winding in the most basic transformer, but till now we have not discussed it. Now we are coming to second winding in the transformer. Supposing one separate winding is brought nearer to the first winding, then this second winding gets linked with a portion of varying flux of first winding. Due to this varying flux linkage, there will also be an induced EMF across it. This induced EMF would be quite small as because the flux linkage is small. Hence, rate of change of flux linkage is also small, and according to Faraday's law, induced EMF across a coil is directly proportional to the rate of change of flux linkage. If now we connect a closed circuit across the second winding, you will get a very tiny current through the circuit provided the second winding is placed much nearer to the first. So we have seen that some portion of the input power is transformed to output through the second windings. This is because some portion of generated flux of first winding is linked with second. Now if we want to transform maximum flux of first winding to second winding, this is done by placing a low reluctant magnetic core in between these windings. Steel is a well-known low reluctant magnetic material. So we would normally use steel for making low reluctant magnetic core in the transformer. As soon as we place a steel core in between these windings nearly, the entered flux which was surrounding the first winding will be concentrated inside the core and linked with the second winding as nearly the same flux linked with second winding. Now the rate of change of flux with respect to time is equal in both windings. Since as laws of electromagnetic induction induced EMF across a conductor is directly proportional to the rate of change of flux linkage, the voltage induced per turn in both windings will be the same. We have already explained that voltage induced across the first winding is the same as a supply voltage actually there. We consider that there is no voltage drop between supply terminals and the first winding. This is an ideal case for theoretical purpose. We will consider that condition as this first winding is connected with supply. It is referred to as primary winding. Now, if this primary winding has n1 number of turns and supply voltage or adduced voltage across primary winding is V1, that voltage per turn in the primary winding is V1 by N1. So far, we have understood that exactly this V1 by N1 voltage will appear across each turn of second windings. So, if the second winding has N2 number of turns, then total voltage across the second winding is N2 into V1 by N1. And let us say this is V2. If now any closed circuit is connected across the second winding, it is provided voltage V to across the circuit. And due to the voltage there will be current flowing through the circuit. Normally, in a transformer, the second winding is connected with load circuit. This winding is referred to as secondary winding if the number of turns of second winding is not equals to that of primary winding. That is, if N2 is not equals to N1, then secondary voltage of transformer is different from primary voltage. Now, if N2 is greater than N1, the secondary voltage will be more than primary voltage. And this type of transformer is called a step-up transformer. On the other hand, if N2 is less than N1, the secondary voltage is less than the primary voltage. This type of transformer is called step-down transformer. This is the most basic theory of transformer. Hope you are understand very well. Thank you.